class, so today I'm going to go over a few examples of hypothesis testing on proportions. In my last video, I covered hypothesis testing on means, so I want to make sure you had some good examples of when you're working with proportions. So a friendly reminder that when we're working with proportions, how we calculate our z-score is a little bit different. Because when we're working with proportions, we really don't have a standard deviation, we don't have a mean. So our z-score formula is going to be p hat, so that's our sample proportion, minus our population proportion over the square root of p, my population proportion, times 1 minus p over n. So this is our new formula for z-score when we're working with proportions. Okay, and again, you don't have to memorize this formula, you just need to know when to use it. So let's take a look at example 1. A new car was designed on the assumption that 60% of its sales would be to female customers, and thus the advertising campaign was particularly tailored to the women. A random sample of 500 purchasers from across the U.S. was selected, and it was determined that only 40% of them were women. Is this number significantly lower than anticipated, indicating that perhaps it might be necessary to change our advertising strategies? This is definitely something as a car maker I could ask myself. So the first thing we want to do is notify the key players in here. So here's what we thought our population proportion was going to be. We know it's a proportion because it's a percentage. We can write that as a decimal. So this is our population proportion. Okay? Our sample size is 500. And our sample proportion from our study found that 40%, so 0.4, were women. So that's going to be our p hat. The first thing I want to do is define my null hypothesis and my alternate hypothesis. So it's important to note that our null hypothesis is going to be equal to what the stated claimed value was going to be, right? There's no change. We say we're trying to prove that this is not the case. My alternate hypothesis is that the proportion is actually less than 0.60. Okay? Is this number significantly lower? Lower would be less than. This makes this a left-tailed hypothesis test. So we're going to be looking for the area in our left tail. So here's 0.6, here's 0.4. What's the area over here? So I'm going to do that by finding my z-score. Okay, so my z-score is going to be my sample proportion of 0.40 minus 0.60 over the square root of 0.60 times 1 minus 0.60 over our sample size, which was 500. So this is how I'm going to calculate my z-score. Be really careful when you're putting this into your calculator that you are following PEMDAS rules. Remember, you are smarter than your calculator. So I have a z-score of negative 9.13. Okay? Now, that's my z-score. I go ahead and I look this up in a z-table. This z-table value is 0.001, right? For any z-score over negative 3.5, we use the value 0.001. Now, because this is a left-tailed test, that's the area in my little tail right here, 0.001. That means it's also my p-value. In this case, our z-table value and our p-value are the same. Now, what I'm looking for in order to show that this is statistically significant is I want my p-value to be less than my significance level. So our significance level is alpha, and alpha can be either 0.05 or 0.01. And if you can use 0.01, that's the one you want to do, right? That means 1 out of 100 as opposed to 1 out of 20. So in this case, my p-value is less than 0.01, right? That's really tiny that this happened by chance. So this allows me to reject H naught at the 0.01 significance level. Okay, So because our p-value is really tiny, so the p-value is low, that means we can reject my HO. That's kind of a saying people see. I've seen it on t-shirts. It exists. All right, so let's take a look at another example. So example 2. Typically 10% of all high schools' Magic Turtles, this is a brand of calculator, have defective on-off buttons. A new set of 40 Magic Turtles rides, and 7 of the 40 are bad. Is this new set significantly different than normal? Okay, so what are my key pieces of information I need to take from this question? The first one is typically 10%, so 0.10, that's our standard population proportion. That's how many of these calculators typically don't work. But then I got a new shipment. So this new shipment of 40 calculators is my sample size, and 7 of the 40 are bad. Okay, so I'm not given a p-hat, but I know how to calculate it. So my p-hat's going to be 7 out of 40. That's the number that don't work out of the total number, and that gives me 0.175. So that's my p-hat. And what I'm asking is the new set significantly different than normal. So I'm not asking, is the new set of calculators, do less of them work than normal? Do more of them work than normal? I'm using the word different. And when I use the word different, that means for my alternate hypothesis, we're going to use a not equal sign. So for my null hypothesis, I have p equals 0.10, right? There's no difference from the claimed value. And then for my alternate hypothesis, I have p doesn't equal 0.10. And what I need to calculate is a z-score. So the first thing to keep in mind before we calculate our z-score is that this is going to be a two-tailed test. Okay, I'm just looking that it's not different. So I'm actually going to have the area. I didn't mean to write mean there. I meant to write p, which is 0.10. Here I've got 0.175. I'm going to have the area in two tails because this is a two-tailed test. So let's go ahead and calculate our z-score and find the area in these two tails. So my z-score is p hat minus p over the square root of p times 1 minus p over n. I'm going to substitute in the values I found. So p hat of 0.175 minus 0.10 divided by the square root of 0.10 times 1 minus 0.10 over 40. And that's going to give me a z-score of 1.58. So remember, this is positive, so it's our value, So it's our value to the left of this value, right? So if I go up in my z-table, I'm going to find a value of 0.9429, right? That's all this area over here. All of this. Now, I'm interested in knowing the area in our tail right here. So I have to take 1 minus 0.9429. That gives me 0.058. So that's the area in this tail right here. But like I said earlier, 0.058. This is a two-tailed test. So now I have to take 0.058 times 2. That'll give me 0.116. This right here is our p-value. The p-value is the area under the curve, the probability of this event occurring by chance. So my p-value is 0.116. Is that less than 0.05? Is that less than 0.01? No, it's a lot bigger. So because our p-value is greater than 0.05, we do not reject our H0. Now remember, in this, when it comes to hypothesis testing, we only have rejection. You either reject the H0 or you do not reject the H0. Okay? So let's take a look at one more final example. So in a Gallup poll of 1,012 randomly selected adults, 9% said that cloning humans should be allowed. use a 0.05 significance level. Okay, so it gave us our significance level this time. To test the claim that less than 10% of all adults say that cloning of humans should be allowed. Okay, so we're already told that our claim is that less than 10% of all adults say cloning of humans should be allowed. So this is going to give us our P of 10. Our sample, of 0.10. Our sample size is 1,012. And our P hat is going to be 0.09, right? Because it's 9% of the participants in this study. So let's go ahead and write our null and alternate hypothesis. So my null hypothesis is that there's no difference from the claimed value. My alternate hypothesis is that we want to test the claim that less than 10%. So I'm going to have P is less than 0.10. This means I have a left-tailed test. So I'm going to take my Z score, that's going to be 0.09 minus 0.10 over the square root of 0.10 times 1 minus 0.10 over 1,012. And this gives me negative 1.07. So here's my normal curve. Here's our p-value. Here I am at 0.09. I'm trying to find the area in this tail. So I go to my z-table, and I find that I get a z-table value of 0.1423. That's the area under my curve. So this is also my p-value, the probability of this occurring by chance. It's 0.1423. Now, 0.1423 is not less than our significance level of 0.05. So in this case, again, we do not reject H naught at the 0.05 significance level.